Hello students, welcome back to our physics lesson. In the last class we had done about force, momentum, inertia, impulse, and we had conducted a small virtual experiment. So in today's class we are going to learn more about the Newton's laws, Newton's first law, second law and third law. So let's zoom in.
So, did you know that physics is all about how things move and why things move? This is discovered by Sir Isaac Newton, and he lived from 1642 to 1727, and he developed the basic three laws of motion, which is mostly known as Newton's laws of motion, and they are published in the year of 1687. So Newton's first law states that objects will remain at rest or in a uniform motion in a straight line unless acted upon by an external unbalanced force. So now imagine the example in our previous video. Which of these materials is easier to push, a big rock or a small marble? Of course, the answer is the small marble. Why? So heavier the object, the more is its tendency to resist. It is very easy to push the marble, and whereas it is very difficult to push the heavy rock. So the first rule of physics is that things like to stay where they are. So for example, if a body is at rest, it continues to be at rest. It is too lazy to move. And if a body is in motion, it continues to be in motion, unless and until an unbalanced force acts on it. So question to think is that, how does the movement happen? The object at rest will continue to be at rest, and the object at motion will continue to be in motion unless and until an unbalanced force acts on it. In simple words, objects continue to do whatever they are doing unless some external force acts on them. We can also understand this using this simple diagram. If the forces are balanced, there can be two cases. An object may be at rest, or the object will be in motion at a non-zero constant velocity in a particular direction. Don't forget, these two cases remain true if the forces are balanced. This property of every object to resist change is called inertia. Inertia can be classified into three categories: inertia of rest, inertia of motion, and inertia of direction. Certain experiences we have while traveling in a bus on the basis of the law of inertia. Now, why does the passenger move backward when the stationary bus suddenly moves forward? This is due to that the body is at rest when the bus is at rest. When the bus starts all of a sudden, the lower part of the body is in contact with the vehicle that starts moving, whereas the upper part of the body continues to be at rest because of the inertia of rest. So you see here that there is a feeling of backward jerk because the upper part remains at rest and the lower part which is in contact with the bus starts moving. Similar example, so this property of any body, we call it as inertia of rest. Similar example of inertia of rest can be taken when we take a ball and a cardboard and a glass, and we suddenly remove the cardboard and we see that the ball falls down. So you see here that the ball falls because it has the inertia of rest. It doesn't want to move along with the cardboard. It has its own tendency to be at rest. So this is a second example of inertia of rest. Have you observed what happens when the moving bus stops suddenly? Pause the video and think for a while. So the question is, what happens when the moving bus applies brakes? With the application of sharp brakes, the passenger tends to fall forward. And this is due to the inertia of motion experienced by the upper part of the body. Bus is moving, the whole body of the passenger is in the state of motion, while the legs which are attached to the contact of the bus stops. And hence the persons or the passengers feels a forward jerk while the bus stops suddenly. So these are examples of inertia of motion, where we can see that the tendency of a moving object remains to be at motion unless and until an unbalanced force acts on it. This is the third example of may have noticed when the car or the bus makes a sharp turn. So for example, the car makes a turn towards right direction, then you may feel the jerk towards the left direction. This is also due to the inertia of direction. Hence we have seen that the inertia of rest, inertia of motion and inertia of direction is directly related to the first law of Newton. Hence, the first law of Newton is also called law of inertia. Provide your own examples of inertia of rest, motion and direction in the comment section. In Newton's first law, we have seen that an object at rest stays at rest and an object in motion stays in motion with the same speed and same direction unless acted upon by an unbalanced force. Now what happens if there is a net force acting on the object? Remember the simple diagram? If the forces are balanced, then the acceleration is zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and same direction. Don't forget, these two cases will remain true only if the forces are balanced. That is, only if the net force is zero. Now let's try to create a diagram for the second case. If the forces are unbalanced, then there will be an acceleration. We saw it in our previous video. Now think of a question. On which two factors do you think the acceleration will depend on? Think carefully. Let me repeat the question. On which two factors this acceleration will depend? Now look at this example that is, you are trying to hit a ball with a particular force. In the first case, you apply a force of 10 units, and in the second case, you are applying a force of 30 units. Please note the acceleration that is created on the ball. So my question is, in which case do you think the acceleration will be more? Of course, the one where the force is more. So you can see that one of the things that the acceleration depends on is the net force. If the net force is more, the acceleration is more. If the net force is less, the acceleration will be less. Now let's investigate the second factor. The second factor, which we call it as mass. Now let's say the man is applying the same force, that is 100 units, to two different carts. One cart has a mass of 50 kg and the other cart has a mass of 100 kg. Which one do you think will have more acceleration? Surely it's the 50 kg one, because it has lesser mass. So lesser is the mass, more is the acceleration. And more the mass, less the acceleration. Hence we can say that mass is inversely proportional to acceleration. We see that acceleration depends on the net force and mass. For the net force, it is directly proportional, while the mass, it is inversely proportional. So mathematically we can write acceleration is equal to net force divided by mass. In other words, we can write the net force will be equal to mass times acceleration. So Newton's second law states that the rate of change of momentum of an object is directly proportional to the unbalanced force acting on it in the direction of the force. Let's verify the mathematical relationship again. So you see here it is change of momentum, and momentum is mass times velocity. So we can write mass times final velocity minus mass times initial velocity is the change in momentum. Then we will also see the word rate. If there is a word rate, then it is related to the time. So its denominator, we have time. It is also told that it is directly proportional. That means we will give the sign of directly proportional. Unbalanced force. We'll pick up the word unbalanced force and hence we will write F or F net. So we can further derive that net force will be directly proportional to mass times velocity minus final velocity minus initial velocity divided by time. Now you see here the final velocity minus initial velocity by time is actually acceleration. Okay, that is rate of change of velocity. So we can substitute this as force is directly proportional to mass times acceleration. Clear? So this is again we verify it, the Newton's second law. Now can you calculate the unit of force based on it? So we see that the net force is mass times acceleration. Hence the unit of mass is 1 kilograms and the unit of acceleration is 1 meter per second square, and from here we can derive that since it is the product we can derive the unit of net force which is 1 kilogram meter per second square. And hence we see here that the 1 kilogram meter per second square is equal to 1 Newton. Now 1 Newton can be defined as the amount of force required to give 1 kg mass and acceleration of 1 meter per second square. What happens when two objects interact with each other? Let's see this with an example. What happens when you place an object on a table? The object exerts a force on the table, right? And the table also exerts an upward force on the object. So there are two forces that result from this interaction. The force on the table and the force on the object, correct? So the two forces have the same magnitude but opposite in directions. So these forces are called action forces and reaction forces. So the force exerted by the object on the table was an action force, and the force exerted by the table on the object is called the reaction force. Students, this is only the Newton's third law. So the Newton's third law is every action has an equal and opposite reaction. So whatever action, the action force one object is exerting, there is a second reaction force which is exactly equal in magnitude but opposite in direction. So whenever any two objects interact, there is a force on each object. We may not visually recognize the reaction force sometimes, but it is experimentally proved that every action has an equal but opposite reaction. Let's see a second example. When we swim, we actually push the water back and the water pushes the body forward. In this situation, you can see that the action force and the reaction forces are present, which helps the swimmer to move forward. Now imagine a situation where the bird is trying to fly high. Now my question to you is that whether the Newton's third law apply here? Think of it. Sometimes it is possible that the third law is not so obvious, but you may think that the bird is the only object here. That's not correct. The wings of the bird pushes the air downwards and the air pushes the bird upward. So we can see here also the action and the reaction forces make it possible for the bird to fly high. Now let's see a third example. So Newton's third law states that every action has an equal and opposite reaction. So this example is very important, students. Have a look and think carefully. What happens when a bullet is fired from a rifle? Yes, you are right. It exerts a forward force on the bullet, right? And the bullet also exerts an equal but opposite force on the gun. So this results in the recoil of the gun. A perfect example of Newton's third law, isn't it? The question to think, students, is if the force exerted by the gun on the bullet is same as the force exerted by the bullet on the gun, why does the gun recoil at the same acceleration as the bullet? Think about that. Gun recoils, yes, you are right, but it does not recoil at the same acceleration as the bullet. So both the action and the reaction forces are the same, isn't it? But the bullet and the gun have different acceleration. If you have understood the second law of Newton, where we have learned that the net force is equal to mass times acceleration, the reason of the recoil velocity versus the velocity of the bullet difference in velocities should be clear. But let's revise. So you see here that the net force is equal to mass times acceleration, is according to the second law. So here you can see that the force of action is equal to the force of reaction. You can see here that the action force will be equal to mass of bullet times acceleration of bullet, and force of reaction or reaction force will be equal to mass of gun times acceleration of the gun. So here you can see that if mass is more, acceleration has to be less, isn't it? So here if you recheck your example, since the mass of the bullet is less than the gun, so acceleration of the bullet is much greater than the acceleration of the gun, and hence the recoil exerted or experienced gun is very less as compared to the bullet.
So students, here we come to an end of our today's class. I hope that you have understood about Newton's laws of motion and the examples. Don't forget to write about your own examples under the comment section. In the next class, we'll do some challenging questions on Newton's laws. So stay tuned. Thank you for watching.